Last time we saw how a signal can be built out of individual sinusoids. If you missed that video or any in this series on fixing your FFT, you can find the whole playlist by clicking on the info card up there in the corner. But are those sinusoids the fundamental Lego bricks of a signal? Or can we break them down still further? Sine waves and cosine waves are both sinusoids. The only difference between them is their phase. A cosine wave is a sine wave that has been shifted by 90 degrees. But here's the thing. If we add together a sine wave and a cosine wave with the same frequency but different magnitudes, we get a sinusoid with the same frequency, but a different magnitude and phase. Therefore, any sinusoid can be broken down further into the component cosine and sine waves making it up. So the Lego bricks of this signal are a cosine wave and a sine wave. But given a signal, how do we find the individual sinusoids making it up? One way of doing it is by using a method called convolution. Here's our signal. Say we want to know if it contains a sinusoid with a frequency of 182 Hz, and if so, what the properties of this sinusoid are. We take the signal and overlay it with a cosine wave with a frequency of 182 Hz and a magnitude of 1. This is a cosine wave, so its phase is 0 degrees. Let's call it the test wave. We multiply the signal by the test wave, giving us this multiplied graph. We then find the area underneath the multiplied graph using integration. This gives a score that tells us how well matched the cosine wave and the signal are. The score is non-zero, so it appears that there is a 182 Hz sinusoid in this signal. But what is its phase? To find out, we slide the test wave over the signal by changing the test wave's phase. As the test wave slides over the signal, we keep recalculating the score. See how the score changes. At some point, the score reaches a maximum before falling off again. Once this maximum is reached, we have found the phase of the 182 Hz sinusoid within the signal. So now we know 2 out of 3 properties of the 182 Hz sinusoid. We know its frequency and we know its phase. But what about its magnitude? Well, the score is proportional to the magnitude. However, it's not necessarily equal to it. To work out the magnitude of the sinusoid, we need to divide the maximum score by the period of the signal. This particular signal repeats once per second, so we divide the score by 1. In this specific case, because the period is 1 second, the score is actually equal to the magnitude of the original sinusoid within the signal. Okay, so I've found the 3 properties of one of the sinusoids in my signal, but there are 40,000 sinusoids in this signal. If I have to convolve each sinusoid over the whole of my signal and try and identify the maximum score, we're going to be here for a very long time. Isn't there a quick way of doing it? Remember, we can break down any sinusoid into its component cosine and sine waves. If we trace how the score changes as we slide the test wave over the signal, see what function it describes. This is a sinusoid. In fact, it's the sinusoid we are looking for within our signal, or at least a sinusoid whose magnitude is proportional to it. If this is the case, because this sinusoid can be generated by adding together a cosine wave and a sine wave with the same frequency but different magnitudes, all we need to do is find the magnitudes of the cosine and sine waves making up this sinusoid. Therefore, instead of performing the whole convolution operation, sliding the test wave over the whole signal, all we need to do is set the test wave's phase to 0, making it a cosine wave, and perform the multiplication and integration once to get the score for the cosine component. Then shift the test wave along the x-axis by 90 degrees so that it becomes an inverted sine wave, and perform the multiplication and integration again to get the score of the sine component. If you're wondering why we invert the sine wave, This has to do with a property of convolution, which I explain in more detail in the online course. So in only two multiply and integrate operations, we've isolated the properties of one of the sinusoids in the signal. Now all we have to do is repeat this another 39,999 times at different frequencies, and we'll have computed the properties of all the sinusoids in the signal. But hang on a second. What happens if a particular frequency doesn't exist in the signal? If a frequency doesn't exist in the signal, like 50 Hz for example, when we convolve a 50 Hz test wave over the signal, the score will always be 0, no matter what the phase. So the magnitudes of the cosine and sine components will also be 0. So how do we know which frequencies to test? Well, that depends on which frequencies your signal is made out of. But isn't that just what we're trying to find out? We appear to have a bit of a chicken and egg situation here. So we're going to have to make some assumptions about our signal. This is an audio signal, so we could limit ourselves to the human hearing range, 20 Hz to 20 kHz. Let's try that and see how we go. But this begs another question. What should be the next frequency we test after 20 Hz? This signal repeats every second, so its period is 1 second. Frequency is equal to 1 divided by the period. 1 divided by 1 is 1. So let's try testing frequencies that are 1 Hz apart from 20 Hz all the way up to 20 kHz. To list out all the magnitudes of the cosine and sine components in a table is not very helpful, as there are rather a lot of them. But if we plot them on two graphs, with the frequency on the x-axis and the magnitude of the cosine component on the y-axis of one graph, and the magnitude of the sine component on the y-axis of the other, this is what they look like for our signal. However, even if we take all the cosine and sine components in this signal from 20 Hz to 20 kHz and add them together to recover the signal, something strange happens. If I play you the reconstructed signal, Fourier, 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 although it sounds almost the same as the original signal, its volume is not quite right. Here's the original signal, Fourier, and here's the reconstructed signal, Fourier. It's too soft. The reconstructed signal is only half the volume of the original signal. We're missing half the energy of the signal. But where can it have gone? It can't be in the higher frequencies. They're too high for us to hear. And it can't be between 0 and 20 Hz, as those two frequencies are too low for us to hear. So where can it be? Have we made an error in our calculations?